to the One World Combinatorics Onwards seminar. Our speaker today is Finn Lidbetter, who's in Waterloo. He's going to speak to us about an improved bound for the Gerver-Ramsey collinearity problem.
Okay, yeah. So yeah, thank you so much to the organizers for the invitation to talk to you today, and yeah, thank you all for attending. Yeah, I'm Finn. I'm currently working as a software developer at a company called Rideco in Waterloo, working on vehicle routing problems with some combinatorial optimization in there, working with map data and all that. But yeah, no, I'm pleased to have this opportunity to get back to a problem that I worked on during my master's degree some 5 or 6 years ago. Yeah, and to tell you about this and yeah, the connections that it has to combinatorics on words and yeah, some computational geometry in here as well. So yeah, let's go ahead and get started with defining the problem we're interested in. So we're going to take S to be a finite subset of Zn, and we say a vector sequence Zi. It's an S-walk if and only if each of the differences between consecutive vectors in that sequence, they're an element of S. So, and the question we're going to be interested in answering is, yeah, for a given set S, what is the longest S-walk we can construct that avoids having M collinear points? Okay, so just avoiding points that have straight lines intersecting. Yeah, too many of them. So yeah, let's motivate this with an example. So let's start simple. Here we just have S is the set ij, the orthonormal unit vectors in 2-space. And yeah, this is an example of a longest S walk avoiding 3 collinear points. So we're just taking steps on I and j, and you could see if we took another step I here, we would get 3 collinear points along this line. And if we took another step j, we'd get 3 collinear points along this line. So yeah, this is as long as we can go for an S walk for this set of S that avoids having 3 collinear points. And yeah, let's take it one step further. If we wanted to avoid 4 collinear points, this is an example of a maximal S walk avoiding 4 collinear points. Again, if we took another step with the I vector, yeah, we'd get 4 collinear points along this line here. This is y equals a half x. And then if we took another step in this direction, we'd get 4 collinear points along here. Okay, so yeah, the 2-dimensional case, yeah, that was studied earlier, and yeah, there's a result from Ramsey in 1977 that yeah, for any positive integer k, there exists a walk such that there exists a walk of length n of k that must have at least k collinear points. So yeah, that's to say there's no infinite S walk where S is a subset of Z2 that avoids having k collinear points. And yeah, there's a related sequence in the done in the OEIS. If we take a of n, it's the smallest integer t such that every length t walk is guaranteed to have at least n collinear points, then yeah, that is this sequence here. So this 4 here corresponds to this case here. So if we have, if we take 4 steps, so if we added a 4th step here, we'd be guaranteed to have 3 collinear points. So a of 3 is 4. And similarly, a of 4 is 9. We have 8 steps here. If we took one more step, we'd be guaranteed, if we added a 9th step, we'd be guaranteed to have 4 collinear points. And yeah, there's a result from Gerver in 1979 that shows that this function grows faster than any polynomial function of n. So yeah, that's a little bit said about the 2-dimensional case. So yeah, the next natural thing we might consider is, what about in 3 dimensions? And the question we might ask is, is there an infinite S walk for S now subset of Z3 that can avoid k collinear points for some k? And well, yeah, there's maybe some spoilers in the abstract for this talk. The answer is yes. This is the main result we're going to be talking about and trying to improve. There is an infinite S-walk for which no 5 to the 11 plus 1 points are collinear. So yeah, 48 million, more than 48 million. So yeah, we're going to see if we can work towards improving on that. But first, let's talk about how they did this with showing their construction. So a little bit of notation. Just A and B here, these are sequences of vectors. We're going to define a few operators. So RA, this is just the reversal, so just reversing the terms. We have AB, just putting them in parentheses like that. That's just the concatenation of those sequences. And for a vector operator, beta, if you apply it to the sequence, it's the same as applying to each of the vectors in that sequence. Okay, and yeah, we're going to be interested in two vector operators in particular, alpha and beta. So alpha just maps I to j, j to I, and k to itself, whereas beta maps I to itself, j to k, and k to j. And using these operators, we define the sequence as follows. So we'll show a bit more about what this actually looks like. But yeah, various operations that apply the vector operators, some reversals, and combinations of those. And then the S-walk, just to state it formally, we just take the vectors that we get from applying these operations recursively, and then just adding up the vectors. Like each of these is going to be one of the unit vectors. The S-walk just gets, we get that just by adding them all up. Okay, so yeah, that's this is what it ends up looking like. Again, not particularly, it's hard to tell anything from that, but I've got a GeoGebra plot here that I'll just switch over to now, just so we can get a sense of what this looks like. It's just a path that, meanders back and forth in this direction. This is just the first 49 terms of the sequence. Okay, so let's get back to this. There we go. Okay, and so let's talk about the main result here. What we're going to be working towards showing is that there exists an infinite walk for which no 189 points are collinear. And the approach we're going to use is we'll take the same construction. We're going to restate the walk as the fixed point of iterating a morphism. And the main other thing that we'll take advantage of that was less available back in the late 1970s is we're going to throw a lot more compute power at this problem. So let's start by talking about the approach that Gerver and Ramsey used to show the point that their sequence avoids these 5 to the 11 plus 1 collinear points. So the approach we're going to use is, we want to show that a pair of points that are separated by a relatively small number of indices cannot be collinear with another pair of points that are separated by a relatively large number of indices. Okay, and then, this will let us establish that bound. And we're going to work with the projection of the points onto a plane perpendicular to I plus j plus k, and this will just provide a way to achieve this bound. So what do we get when we project those points? If we look just at a set of 7 to the n of those points, we find that yeah, for this projection, they will lie inside a trapezoid with base length 4 to the n times this constant factor of gamma. And yeah, we're going to you can take it on faith that they do lie in these in these trapezoids. The projection of these points do lie in these trapezoids. And yeah, we're going to identify these trapezoids as, this is the 0th trapezoid of order n, this is the first trapezoid of order n, this is the second trapezoid of order n. And yeah, the first 7 to the n points will lie within one of these trapezoids of the 0th trapezoid of order n. And then the next 7 to the n will lie in the first trapezoid of order n, etc. So again, I'll return to that GeoGebra diagram here, and this is more or less looking along the projection of this is more or less the projection onto I plus j plus k, and you can get a sense of these where these trapezoids might be overlaid. So you see these first 7 points here lie within a trapezoid here, and then the next 7 here would be within this trapezoid, and then they all lie within a larger trapezoid. This would be a trapezoid of order 1. These are the individual points, so these are the trapezoids of order 0. So yeah, hopefully that gives some insight there. Okay, and then to get a sense of how these actually fit together, I've got this a picture of trapezoids of order n inside n plus 1 inside order n plus 2 inside order n plus 3, and it continues like that. And what you can show is that it's not too difficult to show by induction, as Gerver-Ramsey did in their work. There's only 3 ways that the trapezoids of order n can fit together inside trapezoids of order n plus 1 relative to one another. 2 consecutive trapezoids of order n plus 1 can be arranged relative to one another in just these 3 different ways, up to rotations and reversals. So for the purpose of the geometries that we're going to be working with, these are the only 3 configurations that we need to consider, at least for this, for the approach used by Gerver-Ramsey. I see something. Oh yeah, thank you for sharing that that link in the chat, so you can take a look for yourself. So yes, we're going to then define 2 quantities here for operating on a vector in this walk. So we have z parallel. This is just the sum of the x, y, and z components, and then this is z perpendicular. This is the component of z perpendicular to I plus j plus k. It has length. It has length proportional to this value, and using that factor of gamma that we had from earlier. And we're going to rely on 2 key facts here. So first is that the parallel of 2 differences. The difference between 2 vectors here is just the difference between their indices for where zp and zq are in points in the walk, or vectors in the walk. And if we have 4 vectors, u, v, r, and s, and they are all collinear, then these 2 ratios will be equal. This is kind of like a rise over run style equality here. Like these ratios, these vectors relative to one another, they're going to need to have the same slope in order for them to be collinear. So this z perpendicular, this is going to be the distances of those between points in those projections, if we're just working with that projections. So so let's talk about then how we can get bounds on this quantity. And this will help us towards showing that, yeah, we cannot have a pair of points collinear that are separated by a relatively small number of indices cannot be collinear with a pair of points that are separated by a relatively large number of indices. So we're going to take P and Q to be bounded between 7 to the n and 7 to the n plus 1. And in terms of the projections into onto the plane and in these trapezoids, what this means is ZP and ZQ, they can't be in adjacent trapezoids of order n minus 1. Like they're too far apart. They're 7 to the n indices apart, so they can't be in adjacent trapezoids of order n minus 1. Similarly, due to the upper bound here, the projections of ZP and ZQ, they either have to be in the same trapezoid or adjacent trapezoids of order n plus 1. And we're going to use these two facts then to get upper and lower bounds on this quantity. So yeah, the exact workings out here are not important, but we can get a lower bound just by looking at the smallest distance that we can get between two non-adjacent trapezoids. In this case, it's going to be something like this example here. We have this trapezoid and this one. This is an example of the closest that two trapezoids can get, two non-adjacent trapezoids can get. And if we're in, so that gives us lower bound if you just work out the geometry of this, and the upper bound, this comes from, that's the projections of ZP and ZQ are in the same trapezoid or adjacent trapezoids of order n plus 1. Well, the furthest apart that you can get is 2 base lengths, and so that corresponds to the upper bound. And yeah, if we then use, just manipulate inequalities here, we get upper and lower bounds on this ratio. Okay, so that's for if we have a bound on P and Q. We'll do the same trick with some pair of points ZR and ZS, indices R and S, but bound it between 7 to the m and 7 to the m plus 1. We'll use that second fact that, if they're collinear, this equality must hold true. And manipulate those inequalities, and what shakes out at the end is we get that m minus n has to be at most 10. And so, from this bound, we can actually establish a bound on the number of collinear points in W. So we get that this ratio must be at most 7 to the 11. And if you've got your P and Q are separated by 7 to the n indices, then you know that you can only have so many of those points that are separated by that small amount before you get a pair at the extreme ends that are separated by the larger amount. That's like 7 to the n plus, I guess, 11 here. Yeah, so that's good. That immediately establishes a bound of 7 to the 11. But if you recall the result from the Gerver-Ramsey paper was 5 to the 11 plus 1. So how do we get that improvement? We're going to return to the geometries of the trapezoids here, and suppose that X is a set of collinear points in W with all points in X inside a trapezoid, like the projection of those points are in a trapezoid of order n, but not within a trapezoid of order n minus 1. Then from the result from the previous slide, we know that no 2 points in X can be in the same trapezoid of order n minus 11. Otherwise, we would have 2 points that must be too close to one another and also too far apart from one another simultaneously. So what we can do is, if we again look at how these trapezoids of order n fit inside trapezoids of order n plus 1, sorry, I guess n minus 1 within order n is how I wrote it here. We can see that there's no way to draw a line through this that intersects more than 5 trapezoids. You can get a line through, say, these 5 here, or I guess, only these. You can get a line through these 5 here, but you can't get a line through 6 of these trapezoids. And so if you apply this, at each level, we know that we can't get more than yeah, any 5 trapezoids intersected, and we know that we're at least working with 7 to the 11 of these trapezoids once we get down to level n-11. This gives us, yeah, at most 5 to the 11 collinear points in W. Okay, and so that's a sketch of the how Gerver-Ramsey showed yeah, this bound. So how can we improve upon this? Well, first thing is, yeah, there's no need to lump together all values of P and Q between 7 to the n and 7 to the n plus 1 all at the same time. Yeah, we can use a finer partition of this interval to get up stronger constraints on this ratio. So that's the first thing we'll consider. Next, yeah, if we did this trick of looking at maximum number of trapezoids of order n-1 inside a trapezoid of order n intersected by a single straight line. Yeah, could we do this further? If you look at trapezoids of order n-2 inside a trapezoid of order n, can you get a stronger bound on the number of those that can possibly be collinear if you consider all orientations or configurations of those trapezoids? And thirdly, yeah, everything we've talked about, everything in that approach was just working within 2 dimensions. So could we get improvements by considering the 3rd dimension? And yeah, I should say that all of these were suggested by Gerver-Ramsey in their paper in 1979. But yeah, considering really any of these 3 takes yeah, a lot of yeah, computational power to like just consider all the possibilities. But yeah, so this is the rough approach we're going to take, looking at especially at steps 1 and 2 here. So yeah, let's get to the combinatorics and words application here and start by restating the construction of W as the fixed point of iterating a morphism, and this will make some proofs easier and allow us to yeah, work with it more easily. So yeah, I should say this is due to Luke Schaefer, who's also a master student that worked with Jeff. So yes, this is a problem that yeah, was posed yeah, to a few students of Jeff. I heard talking with Narad, it was also, Jeff also suggested this one to Narad when he was a student there as well. So yeah, pleased to be able to report some progress on this one after a few of us have taken a crack at this. So yeah, this is yeah, let's recall the vector operators that we're working with. We have in the construction used by Gerver-Ramsey. What we're going to do is, yeah, we're looking to construct a morphism that yeah, produces the same sequence. And if we look at our alpha and beta operators, we can see that these act on ijk. Yeah, the operations are similar to that of, well, they act in a way corresponding to the symmetric group of order 3. Using just alpha and beta, you can get each permutation of ijk. And then the reversals, they commute with itself and these operations. And so that corresponds to a cyclic group of order 2. And yeah, the product of these groups just gives the dihedral group of order 12. And so what we'll do is we'll yeah, give a morphism consisting of 12 symbols, 1 symbol corresponding to each element of the group. And yeah, it ends up looking like this. Yeah, 1 symbol for each I, J, and K. The subscript B's just represent applying the reversal or not, so B for backwards, and then the primes correspond to yeah, whether you've applied a one of these alpha or beta vector operators. Yeah, so that's what it looks like. And yeah, showing that these 2 constructions are equivalent is not so difficult. It's just, yeah, induction on, yeah, it's an inductive argument, and you just use the properties of the, yeah, the operations that commute with one another. And yeah. So yeah, I won't show that proof here, but yeah, I trust that it's not so difficult. And yeah, sorry, I guess for completeness, I should also give the yeah, we have this output map to map it to the vectors, and it's in the predictable way. The I, IB, I prime, IB prime, these all map to vector I, and similar for J and K. And yeah, we iterate this morphism and then define the infinite word produced by this as lambda. Okay, so we'll refer to the sequence as lambda going forward. Okay, so yeah, let's remind ourselves of what we wanted to do here. So we want to, again, bound the relative index separation of collinear points. And previously, we just had these few configurations to consider. And yeah, we could get this bound. So what we're going to do is attempt to get sharper bounds by considering splitting this up into these, I guess, 42 different pieces here. Yeah, and we'll see that if we have the difference between P and Q between these bounds relative to C, then this will actually give us that if we have the projection of ZP lying in the kth trapezoid of order n-1, and the projection of ZQ lie either in the K plus cth trapezoid of order n-1 or the K plus C plus 1th trapezoid of order n-1. Okay, so yeah, a couple of different possibilities there. But yeah, also lots of different possibilities for C that we'll have to consider. So yeah, how can we go about getting these bounds? So because we now have to consider trapezoids separated by up to 49 indices and all possible relative configurations that we could have here. So first up, we need to, we'll establish a correspondence between the symbols in lambda and trapezoid orientations. Then yeah, if we can find all distinct subwords of length up to 49 in lambda, that will give us the relative trapezoid configurations that we'll need to consider. And then after that, once we have that, it's just a matter of doing the computational geometry on all those corresponding sequences of trapezoids and getting upper and lower bounds on those distances. So yeah, first step of that, establishing the correspondence. Again, this is just an inductive argument, and we can get the orientation of the mth trapezoid of order n. This is just given by the mth symbol of lambda. And yeah, the order n here doesn't matter. These are all similar to one another. So yeah, it's just dependent on m here as to which trapezoid orientation you have. Okay. The next step, finding all distinct subwords of some length n. And again, this ends up being an inductive argument. We find that the last subword of length 1 occurs at 215, just because that's by index 215 we've seen all 12 symbols. And then if we just look at the morphism, we can see what possible words of length 2 we can achieve. And then after that, it's a relatively straightforward induction to establish this bound. And once we have that upper bound, we can just do a brute force search for distinct subwords up to this last index for any particular n. Okay, and the code for this is publicly available in my GitHub repository here. There's a Java project there and a Rust project as well for some of the other computations. But this is part of the Java project, and for the value we're interested in here, this is, you can issue this within the Java package, and then find the index of the last new subword of length 49 occurs at index 27,334. yeah, it's using a different alphabet here to what we defined earlier for the morphism, but yeah, that's just for convenience. Yeah. Okay, so we got we need to consider potentially words up to index 27,334. So yeah, to get upper and lower bounds on distances, we're going to consider each value of C, and similar for points ZR, ZS. We're going to define distances between trapezoids. So we need to know smallest distance between trapezoids as well as the largest distance between points and trapezoids. So this D here, when it's operating on points, this is the just the Euclidean distance in this projection in the plane. And then we define these values are actually the ones we're going to be interested in. The smallest value across all trapezoids separated by C or C+1 indices. We want to know the minimum and maximum values for those so that we can get our bounds on that perpendicular distance in this projection in the plane. Okay, and so to actually compute this value, again, we're working with different values for n. We need to find a way to be able to compute this for a specific n. And just because the trapezoids are congruent to one another, we can rewrite it as relative to this, like sticking 1 in here. And using the correspondence between symbols in lambda and the trapezoid orientations, we don't need to consider all possible natural numbers. We only need to go at least as far as the index of the last new subword. And we could also only consider those k that correspond to distinct subwords. But this will also work here. So if we do that, this is just another command within that Java package. It works with a symbolic representation of these trapezoids to avoid precision issues when we go through this. But what it spits out at the end is an improved bound here corresponds to having m minus n is less than or equal to 3. Okay, so where previously we got a bound of 10, doing this computation, we immediately get an improvement to m minus n less than or equal to 3. So that's great. This already implies at most 2,401 collinear points, which is a significant improvement over the 48 million that we started with. So this, let's see. But we want to, can we do a similar trick as we applied previously with looking at straight lines intersecting the trapezoids? And so if we assume P and Q again between 7 to the n and 7 to the n plus 1, then no 2 points collinear with both ZP and ZQ can lie in the same trapezoid of order n minus 4. So that's again the same, similar to what Gerver-Ramsey did, but just with n minus 11 instead of n minus 4. And slightly stronger claim is no 2 points collinear with both ZP and ZQ. They can't lie in 2 trapezoids of order n minus 4 separated by more than 2,401 indices, just by similar reasoning. So what we're going to do is find all the ways that 2,401 consecutive trapezoids of order n minus 4 can be arranged, and look for the largest number of them that can be intersected by a single straight line. Okay, so first question, how far do we have to look for new sequences of 2,401 trapezoids? So we use this command again. This time, it's quite a ways into the sequence, index 1,339,414. But yeah, as mentioned previously, yeah, we don't need to consider all of those indices. We just need to look at the distinct subwords. And yeah, there's another command implemented in that package for this. Yeah, distinct subword intervals. So these are just yeah, everything in the intervals not included here. So the intervals in the gaps, every single word starts there has been included in yeah, some other interval, earlier interval. Okay, and if you add these up, there's some yeah, approximately 65,000 different indices to consider. So yeah, not nearly so many as the 1,339,000 here, but yeah, still a lot of possibilities to consider, and yeah. So yeah, let's work towards defining an algorithm for this. So yeah, we want to find straight line intersecting as many of these trapezoids as possible. So yeah, how do we find that line? So yeah, given a set of P of polygons in the plane, if L is the largest number of polygons, largest number of those polygons intersected by a straight line, and we have an example of that straight line, then yeah, then there is another straight line through a pair of vertices of polygons in P that intersects that same maximum number of polygons in P. And we can see that by if you have one line that intersects yeah, those L polygons, you can translate it down until you hit one vertex without leaving any of the polygons. And then once you have that one vertex, you can rotate about the line about that vertex until you hit another vertex, again, without leaving any of the polygons. Okay, so this gives us an algorithm. For each sequence of 2,401 trapezoids, we can consider each pair of trapezoid vertices to enumerate all candidate lines. And then for each candidate line, we can iterate over those same trapezoids to determine how many of them are intersected by that line. Unfortunately, this algorithm is going to be a bit too slow. Yeah, this is of n squared different pairs of vertices, and then iterated over again O of n cubed. If we've got 65,000 of those to consider, we're talking about, yeah, I guess, I think we're up into the hundreds of trillions of operations here. So, yeah, but yeah, fortunately, we can do better. So yeah, what we can do is instead use a radial line sweep approach. So consider each vertex as a pivot, and we sort all the trapezoid vertices like radially relative to that pivot, and then only consider trapezoids that are within 2,401 indices of the pivot vertex, and we'll imagine rotating that line around that pivot vertex and keep track of yeah, the current set of trapezoids intersected, and each time the line moves to the next vertex, like radially relative to the pivot, we'll either exit a trapezoid or enter a new one. And so we can keep track of the count of trapezoid intersections. Okay, so, but yeah, we're going to have to efficiently keep track of potentially multiple counts here. Yeah, one count for each possible interval of 2,401 trapezoids. So yeah, when the line enters a new trapezoid, we're going to have to account, increment the count for all intervals that trapezoid falls within. Again, we don't want trapezoids that are more than 2,401 indices apart to be influencing the count. So yeah, we need to keep one count for each interval of 2,401 consecutive trapezoids. So we'll need an increment operation and a range decrement operation. And also when the counts are incremented, we'll need to yeah, check that all of those values that are incremented to see if we've achieved a new maximum value. So to do this, we'll use a segment tree data structure. Yeah, that will just give us sufficient these range update and range query operations. And so, yeah, this will give us an improved algorithm. So, yeah, for each pivot vertex and interval size, yeah, let's see. Yeah, we can construct a segment tree with n O of n leaf nodes. This has cost O of n. Sorting the trapezoid vertices relative to the pivot vertex. We've got an n log n operation here. And then, yeah, iterating over those O of n vertices. And for each one, performing a range update and a range at most one range query. Yeah, overall, this step is also going to be n log n. And then, yeah, for this improves what previously was O of n cubed down to n squared log n overall for all of the yeah, trapezoid, for all of the indices that we'll need to consider. And then, yeah, still multiplied by that factor of 65,000 for each of the distinct subwords that we'll need to consider. So, yeah, again, this is all implemented as a command in that Java package. Count the collinear trapezoids separated by at most 2,401 indices. And then, yeah, this gives the number representation to use. This is the symbolic representation. Yeah, I should say, yeah, this commands were also implemented in using like a floating point representation, just to be able to, yeah, that's a slightly simpler one implementation, just as a way to check it. But yeah, hole in root 3. This is a symbolic representation. That means we don't need to worry about precision issues. All calculations are done in integers. And so, yeah, if we run that command, we find, yeah, the largest number of trapezoids separated by at most 2,401 indices and separated by and intersected by a single straight line is 188. And you may recognize this number from the result we were working towards. So yeah, that's what we were driving at. So yeah, that's good. And yeah, I can't show what it actually looks like for 2,401. The details get a little too fine to really get anything meaningful from looking at it. But here's an example of the maximum count of 343 consecutive trapezoids intersected by a straight line. Yeah, it's just this line here, and there are 62 of those trapezoids. But yeah, the image for 2,401 is very similar. It's this, like, if you just imagine iterating this one more time and putting 7 trapezoids within each of these and then shifting it down to that baseline, that's what it looks like. Okay, great. So we have the bound on the number of yeah, 188 collinear points advertised in the theorem. Yeah, are we done? Unfortunately, there was one detail overlooked here. Yeah, the eagle-eyed among you may have noticed, yeah, at some point earlier on, we were working with these. We bounded P and Q by between 7 to the n and 7 to the n plus 1. And yeah, we then started working with trapezoids of order n minus 1. This doesn't work if n is equal to 0. And yeah, if we then work through the same steps for n equals 0 case, even taking advantage of even the specific geometries that we have when you go down to n equals 0, you're working with the points and lines directly rather than the trapezoids themselves. What happens is we get this bound, m minus n is only less than or equal to 5 here in this case. And then, yeah, this gives us, in this case, at most 7 to the 6 collinear points, where previously we had 7 to the 4. And yeah, it might not be so easy to do the number of if we try to look at 7 to the 6 consecutive trapezoids intersected by a straight line, that's really pushing the limits of what we might be able to compute with the previous approach, even with the improved algorithm there. Yeah, so we might need a different approach, as we don't want to throw away all the hard work that we did to get to 188 in the other case. So here is where we take a different approach, and yeah, as part of this project, I did a long-running computation looking at the first 10 million points of W. Yeah, there are no 7 collinear points. There are examples of 6 collinear points. Yeah, so yeah, this was just brute force computation considering essentially all lines that you could draw between pairs of points in the first 10 million. And yeah, this was long-running computation that took ran over the course of a few months. But yeah, running in parallel, it took something like 2 years and 9 months of CPU time in total. But the important result to get from this actually is this number 10 million is chosen because it's just a little bit more than the index of the last new subword of length 7 to the 5. And so, yeah, from that, we get that in every 7 to the 5 consecutive indices of W, there are no 7 collinear points. This can actually also be computed more directly and far more efficiently. You can do it in about 30 minutes of computation. I think this is in the Rust project within that GitHub repository that I shared. There's a command there for getting this bound, like looking at all of the distinct subwords of length 7 to the 5 and looking at how many of them, looking at collinear points, the maximum number of collinear points you get there. And yeah, so from this result, we can actually establish that if we then if we know that every consecutive 7 to the 5 indices has at most 6 collinear points, then in any 7 to the 6 consecutive indices, well, there's 7 of these intervals of length 7 to the 5. Each of those can have at most 6 collinear points. So we get then at most 42 collinear points. And so, yeah, this then reestablishes the bound. We've handled the n equals 0 case, and we've got a value that's less than that 188 that we got in the other case. So yeah, that's great. This proves the theorem. Okay, but yeah, we should consider, can we push this any further using these techniques? So the first thing to consider is, can we improve the bound by considering lines through trapezoidal prisms in 3 dimensions? Taking advantage of the 3-dimensional aspect of this. So yeah, this is a variant on the stabbing line problem in 3 dimensions. We'll have a set of trapezoid, like 3-dimensional polyhedra, these trapezoidal prisms, and we'll be looking for the largest number of them that can be separated by a certain number of indices that are intersected by a single straight line. There is an n cubed log n algorithm for finding O of n cubed candidate stabbing lines, and we could adapt that to then find the largest number of those, finds those candidate lines, and then iterate through them to see how many are intersected. But this is going to end up being far too slow. We had n squared log n previously, and that's starting to push it. This computation for n equals 2,401 is going to be in the quadrillions, I think, quadrillions of operations. So I think that's a little bit too far there. So that's one way to improve it. But I think that might be out of reach for now. The other thing we can do is, could we use a finer partition of the gaps between ZP and ZQ, or the indices between P and Q. And for this, yeah, it seems unlikely. Like to get an improvement, yeah, previously we had m minus n less than or equal to 3. To get an improvement, we'll have to get it all the way down to less than or equal to 2. And yeah, this is the value we'd be shooting for. And yeah, I computed these values for, yeah, a couple of options for finer partitions here. I was not able to push the computation as far as this one, and it looks like even if we were, it looks unlikely to yeah, get an improvement to reach the value that we'd need to. And yeah, even if we did, I think there are also, you might have to do more work in the n equals 0, n equals 1 cases to improve that as well. I think once you start considering these finer partitions. Yeah. So yeah, that's where we'll leave it for that result. But yeah, we can then ask some open questions. So first, yeah, can the bound be improved further? Like, is 6 the largest number of collinear points in this particular walk? We then can ask, yeah, if we're still considering walks in 3 dimensions on I, j, and k, yeah, could we find a different walk that has fewer than 6 collinear points? We can also ask, yeah, can we do better in higher dimensions? Can we avoid 3 collinear points if we go to yeah, 4 or higher or even more dimensions? And then yeah, last I'll say yeah, considering also the 2-dimensional case, we've only got 6 terms in this sequence. Yeah, it would be interesting to compute more terms of that sequence. Yeah, so I'll end it there, and thank you very much for your attention. And yeah, if you have questions, I'd be happy to try to answer them.
Oh, thank you so much, Finn. Yeah, does anyone have any questions? So is it sort of obvious how Gerver and Ramsey constructed their sequence in the first place to have these properties?
For that, I'm not actually sure. It's not apparent to me. Yeah, I don't actually have a good answer for that one.
Because I guess they must have like designed it by hand somehow.
Yes. Yeah. Yeah, I don't actually have a good sense because yeah, if I were to do this, it would be these days I would yeah, try some things and then find a candidate and then throw a computer at it to see if it is a good candidate. But yeah, I'm not actually sure how they did this.
Right, but somehow they stumbled on what apparently is the optimal construction.
Yeah, or a construction that at least yeah achieves. It might not be optimal for in 3 dimensions. They might be able to do better than 6 collinear points, but
Do you think
yeah.
they can? Do you think better than 6 is possible?
I don't know. I don't have a reason to think that 6 is the yeah, that's the yeah, the limit here for 3 dimensions. In fact, I think there was a note from their paper that they suspected that it had fewer than it only had 3 or 4 collinear points. It was only yeah, by computing more terms and going out to that index. I can't remember what that where that first example of 6 comes, but it's something like 185 or more terms into the sequence. So I think they initially even speculated it was fewer than 6, but
But it's not.
yeah.
Right.
Yeah. So yeah, sorry, I wish I had a better answer for that question.
No, no. Yeah, it might be cool to try and play around with some other constructions.
Yeah.
Yeah, I have no idea how they came up with their construction in the first place.
Yeah.
Does anyone else have anything to ask? If not, Yeah, thanks again, Finn.